Hi everybody, welcome back to Trigonometry. Today we're in section 1.4, using the definitions of the trigonometric functions. In this section we'll talk about the reciprocal identities, we will talk about the signs and ranges of the function values, and we'll take a look at the Pythagorean identities and the quotient identities. So here we go. First, let's take a look at the reciprocal identities. We kind of already know these, but when we saw them in section 1.3, we wrote them in terms of x, y, and r, and today we'll write them in terms of each other. So you'll see what I mean here. For all angles theta, for which both functions are defined, the following identities hold. The sine of theta is equal to 1 over the cosecant of theta. Now you know 1 over something is just another way of saying it's the reciprocal, and we already knew that the sine function was the reciprocal of the cosecant function. So this is nothing new, it's just a new way of writing it for us. So the sine of theta is equal to 1 over the cosecant of theta. The cosine of theta is equal to 1 over the secant of theta. The tangent of theta is equal to 1 over the cotangent of theta. So in every case, these are just reciprocal relationships that we already knew about. And then we can do the same thing for the other three functions. The cosecant of theta is the reciprocal of the sine of theta. The secant of theta is 1 over the cosine of theta. And the cotangent of theta is 1 over the tangent of theta. So again, not new information from what we learned in section 1.3, but just a different way of writing the same thing that we already knew. So let's get an example here. Example 1 says find the cosine of theta given that the secant of theta is 5/3. Well, we know that the cosine is the reciprocal of the secant. So if the secant of theta is 5 over 3, then the cosine of theta is going to be 3 over 5. Notice here that when we do a reciprocal, the sign stays the same. The reciprocal of a positive number is positive, and the reciprocal of a negative number would be negative. And now in part B it says find the sine of theta given that the cosecant of theta is negative square root of 12 over 2. And again, sine and cosecant are reciprocals. So all we have to do to find the sine is do the reciprocal of this fraction. So the sine of theta is going to be negative 2 over the square root of 12. Now, as you know, it doesn't make any difference if the negative sign is in front of the whole fraction or if it's in the top. But if the negative sign were in the bottom, we would move it up to the top. It's okay to have it either in the top or in the front of the whole fraction. But now we do have a problem with this answer. This is the sine of theta, but it's not in an acceptable form for a final answer. Two things need to happen here. We need to reduce this radical, and we also need to rationalize the denominator. So we can't leave that radical in the denominator. Now it doesn't really matter which one you do first, but you want to make sure that by the end that the radical is in its simplest form and that the fraction is in its simplest form. So I think that what I will choose to do first here is simplify this radical. So we know that 12 is 4 times 3. So the square root of 4 would be 2. That 2 would come outside the radical, and the 3 would stay under the radical. So when we reduce that radical, it looks like this. And of course, the first thing we notice here is that we have a 2 in the top and a factor of 2 in the bottom. So let's go ahead and divide those out. 2 divided by 2 would leave 1 in both places. Of course, we don't really need this 1 in the denominator because that's just a coefficient for this radical, but we wouldn't want to leave the top empty. So there's always a 1 when everything else cancels from the numerator. So now we need to rationalize this denominator, which just means to remove the radical from the denominator. So of course the way to do that is to multiply by the radical we're trying to eliminate in both top and bottom. And so now that gives us negative 1 square root of 3 for the top. So I'll just write negative square root of 3. And in the bottom we have 1 times this square root of 3 times this square root of 3. So that's 3. So the sine of theta is negative square root of 3 over 3. Now let's talk about the signs of the function values. We saw in section 1.3 that the functions can be positive or negative depending on what quadrant the terminal side of the angle falls in. So let's look at that a little more closely. So here we have a coordinate system, And let's think about what happens in quadrant 1. So in quadrant 1, all the x values are positive and all the y values are positive, and as we know, r is always positive. So if you think about the definitions of the functions, like sine of theta is y over r, and cosine of theta is x over r, etc. If all of the x, y, and r values are positive, then all the function values will be positive. So in quadrant 1, all the function values are positive. Now let's think about quadrant 2. In quadrant 2, your x values are going to be negative, but your y values are going to be positive, and of course, like we said, r is always positive. So we know that the sine of theta is y over r, so that would be a positive divided by a positive. So sine would be positive, and of course its reciprocal, r over y, would be positive. But all the other function definitions involve an x. Cosine is x over r, tangent is y over x. Secant and cotangent are just reciprocals of those two. So all of those other functions are going to be negative. So in quadrant 2, only sine and cosecant are positive. The other four functions are negative. And now let's think about quadrant 3. In quadrant 3, we have negative x coordinates and negative y coordinates and positive r. So of course sine will be negative because y over r would be a negative over a positive. Cosine would be negative because x over r would be a negative over a positive. Tangent, however, will come out positive because tangent is y over x, which would be negative over negative, and we know that negative divided by negative is positive. So tangent will be positive, its reciprocal cotangent will be positive, everything else will be negative. And in quadrant 4, we have positive x coordinates but negative y coordinates. So x over r, which is cosine, will come out positive, its reciprocal will come out positive, but all the other four functions will come out negative. Here is a breakdown of what functions are positive and negative in each quadrant. So in quadrant 1, as you can see, all 6 functions are positive. In quadrant 2, only sine and cosecant are positive, the other 4 are negative. In quadrant 3, only tangent and cotangent are positive, and in quadrant 4, only cosine and secant are positive. So now it's important for us to know, without thinking too hard about it, what functions are positive or negative in each quadrant. But this table would be very difficult to memorize. I think we would always be getting it wrong. And this diagram has just too much information in it. We don't want to have to write this all the time. So it turns out all of this information can actually be boiled down into just this little diagram I'm about to draw with you. So draw yourself a coordinate system. And in quadrant 1, write A. In quadrant 2, write S. In quadrant 3, write T. And in quadrant 4, write C. So we've got, starting in quadrant 1, A, S, T, C. Now the A stands for all, because we know that all functions are positive in quadrant 1. The S stands for sine, because we know that sine and its reciprocal are positive in quadrant 2. In quadrant 3, the T stands for tangent, and so that means tangent and its reciprocal are positive in quadrant 3. The C stands for cosine. Now this is the only one where I think some people could get confused, because all of the functions that start with co, of course, have C as their first letter. But what we're looking at here is cosine. So we know in quadrant 4 cosine will be positive, and of course its reciprocal would also be positive. So we have ASTC, and if you need a little sentence to help you remember that, the one that most people use is all students take calculus. All students take calculus. And we will use this all throughout the course to help us determine what functions should be positive or negative in each quadrant. So here is example 2, and it says determine the sines of the trigonometric functions of an angle in standard position with the given measure. And what we're going to do is sketch each angle first so we can see what quadrant it falls in. So an 87-degree angle, of course, would fall in quadrant 1 because it's not quite 90 degrees. So if it falls in quadrant 1, that tells us that all of the function values are going to be positive for this angle. For part B, we have 300 degrees. Now 300 degrees would have to fall in quadrant 4 because it's bigger than 270 but less than 360. So we know that 300 degrees has a terminal side in quadrant 4. If we think ASTC, we can see that only cosine and its reciprocal will be positive for this angle. All the other functions will be negative. And on part C, we have negative 200 degrees. Now, remember, for negative angles, we have to rotate clockwise. So we'll go this direction. So if I go clockwise 200 degrees, I'm going to go past the negative y-axis and a little bit past the negative x-axis, because if I just went from the positive x-axis to the negative x-axis, that would be negative 180. So I need to go a little further to reach negative 200. So now we can see that the terminal side for negative 200 is actually in quadrant 2. And if we think ASTC, we can see that the sine function and its reciprocal will be positive for this angle, and all the other functions will be negative. And here is example 3. This one says identify the quadrant or possibly quadrants of any angle theta that satisfies the given conditions. So in part A, it says the sine of theta is greater than 0 and the tangent of theta is less than 0. Of course, we know that when they say greater than 0, we can interpret that as positive, and when they say less than 0, we can interpret that as negative. So our angle theta is going to fall in a quadrant where it has a positive sine value and a negative tangent value. Now if we think about ASTC, we can see that the sine function will be positive in quadrant 1 and quadrant 2, but it will be negative in quadrant 3 and quadrant 4, so those two quadrants are out. And then out of these two, we need to identify which one will have a negative tangent value. Well, of course, everything is positive in quadrant 1, so quadrant 1 is out, and we can see that theta must be in quadrant 2. So in quadrant 2, the sine value would be positive, but the tangent value would be negative. And then for part B, they want us to find the quadrant or quadrants where the cosine of theta would be negative, and the secant of theta would also be negative. So again, let's think ASTC. And we want to find the quadrants where the cosine of theta would be negative. So let's rule out the ones where it's positive. We know cosine is positive in quadrant 1 and quadrant 4. So those two quadrants are out. And then when we look at this second piece of information, it says the secant of theta is less than 0, or the secant of theta is negative. And of course, that's the same two quadrants because secant and cosine are reciprocals. So having this piece of information didn't add anything to what we already knew. We already knew that we wanted to find the quadrants where cosine was negative. Well, those are the same quadrants where secant is negative. And so we're not going to be able to narrow this down to just one quadrant, and we're going to have to say that theta could either be in quadrant 2 or quadrant 3. Now we're going to change gears a little bit and talk about the ranges of the trig functions. And just a reminder from algebra of what range represents. The range of a function is the set of all y values that the function can give. In other words, it's the set of all the function's possible outputs. So here are some graphs, and let's get the range of each of these functions. So for this first graph, the lowest y value is 0, and the graph goes up forever, so the highest y value is infinity. In other words, there's not a highest y value. So we could write that the range of this function goes from 0 to infinity. Remember, the brackets are used when we want to include a number, and the parentheses are used when we want to exclude a number. Or in the case of infinity, we always use parentheses because infinity is not actually a number we can reach. And now for this middle graph, the graph just runs right out of the window here. So really there should be arrows indicating that the graph continues downward forever. But what we can see here is that there is no lowest y value, but the highest y value appears to be 3. And so we can say that the range of this function is from negative infinity up to 3. Remember, when we talk about range, we're only thinking about the outputs, the y values, not the x values. And for this third function, we can see that the lowest point on the graph will have a y value of -4, and the highest point has a y value of 0. So for this function, the range will be from -4 to 0. And now let's kind of review what we already know about the function definitions. We're familiar with this diagram right here where we have an angle theta in standard position, and we have a point x comma y that's on the terminal side of the angle, and that allows us to draw this little imaginary triangle right here with legs x and y and the hypotenuse length r. And we know that the definition of the sine of theta is y over r, the definition of the cosine is x over r, and of course r is the hypotenuse, which means it's the longest side. Now, let's just think about x and y as lengths. I don't want to consider their sine because it doesn't matter which direction we had to go to reach this point. The only thing we're concerned about is the size or the length of x and y. So because r is the hypotenuse of this triangle, we know that the absolute value of y is less than r, and we know that the absolute value of x is less than r. So just hold on to that idea for just a minute. Now let's think about quadrantal angles. So when you've got a quadrantal angle, the terminal side will either be vertical like we have here or horizontal like we have here. If the terminal side is vertical, then you can always find a point on that terminal side that will be 0 comma something. So I'll call it 0 comma y here. And then r, the distance from the origin to that point, would just be the absolute value of y. If your terminal side is horizontal, then there's going to be a point x comma 0 on the terminal side, and your r, distance from the origin, would just be the absolute value of x. So for quadrantal angles, we either know that the absolute value of x is equal to r, or the absolute value of y is equal to r. So we already saw in the previous slide that for all the other angles, absolute value of x and absolute value of y are both less than r. And now here for the quadrantal angles, we find out that one of them is equal to r. And so we can put all that together and know that for any type of angle we have, the absolute value of x will either be less than or equal to r, and the absolute value of y will either be less than or equal to r. In other words, r will always have to be the largest number. So that means that for all angles, the ratios y over r and x over r must either be a positive proper fraction, a negative proper fraction, or they have to either be equal to -1 or +1, right? Because think about it, we've already figured out that y and x are both smaller than r, or at their very biggest, they're equal to r. So basically, there's no way for these two fractions to be improper. Y over r and x over r cannot be more than +1 or less than -1. And that means that the sine of theta and the cosine of theta always have to be between -1 and +1. If we look at it on the number line, so draw yourself a number line and label the -1 and the +1 on the number line. The sine values and the cosine values have to be between -1 and +1. So we've got brackets here to indicate that they can be equal to either of those values, and then we shaded in between to show that they can be anything in between, but they can't be less than -1 and they can't be more than +1. So in interval notation, we would say that the range of both sine of theta and cosine of theta is bracket -1 comma +1. All sine values and all cosine values must be between -1 and +1. Now let's think about cosecant and secant. So now we're looking at the reciprocal of sine and cosine. The definition of cosecant is r over y. The definition of secant is r over x. So now with r being on top, the big number is on top, and so these two fractions are guaranteed to be improper fractions, which means that they will have a value that is either greater than or equal to 1 or less than or equal to -1. On the number line, it would look like this. We've still got our -1 and +1 labeled on our number line. Now, because we're dealing with improper fractions here, we're dealing with something that's either less than -1 or equal to -1, or it could be greater than +1 or equal to +1. So you see what's happening here. Our secant values cannot be in between -1 and +1 because we have the big number in the top of the fraction. See, that makes these fractions improper. So if they're negative, they can be less than -1, and if they're positive, they can be more than +1, but they can't be in between -1 and +1. In interval notation, we would write the range of both secant and cosecant as parentheses -infinity, comma, -1, bracket, and then union symbol, that union symbol you'll remember from algebra, bracket, 1, comma, infinity. And that's the range of both the secant function and the cosecant function. And now the last two functions that we have left are tangent and cotangent. And of course, tangent is y over x and cotangent is x over y. And there's no r here. So there's nothing that limits the relationship between x and y. There's no limitation on how big x or y can be. Therefore, there's no limitation on the ranges of either of these functions. Therefore, any number can be a tangent value or a cotangent value. If you wanted to draw this on a number line, you'd have to shade the entire number line. And so in interval notation, the range of both of these functions is -infinity to +infinity. And now let's put it all together. So you want to draw yourself a number line and label -1 and +1 on that number line. Now we're not going to do this with the brackets and parentheses and all, but let's just get a visual representation of which functions can exist on which parts of the number line. So we know that for the sine function and the cosine function, they both have to exist between -1 and +1, and they can't go beyond those boundaries. On the other hand, secant and cosecant can't come inside the box. They can either exist to the left of -1 or to the right of +1, but they can't be inside the box. And of course, all four of these can be equal to -1 or equal to +1. And then for tangent and cotangent, they can exist anywhere on the number line. So again, sine and cosine only inside the box, secant and cosecant only outside the box, but then tangent and cotangent anywhere, either inside or outside the box. So let's practice a little bit with example 4. This says decide whether each statement is possible or impossible. And in part A, it says the sine of theta is 2.5. So is it possible for an angle to have a sine value that's equal to 2.5? And we know that sine values have to be between -1 and +1. 2.5 is not between -1 and +1, so it is impossible for an angle to have 2.5 as its sine value. And then in part B, is it possible for the tangent of an angle to be 110.47? And we know that tangent and cotangent can both exist anywhere on the number line, so any number can be a tangent value, and therefore it is possible for an angle theta to have 110.47 as its tangent value. And then in part C, is it possible to have an angle theta so that the secant of theta is equal to 0.6? Well, we know that secant and cosecant cannot exist between -1 and +1. They can be less than -1 or more than +1, but they can't be between. 0.6 is between -1 and +1. Therefore, this is not a valid secant value, so it is impossible for an angle theta to have 0.6 as its secant. And now we're going to change gears again, and we're going to have a look at a type of problem that will come up multiple times throughout the course. And I'll point it out to you as we go along, but this will be our first time to see it. And because we're going to be doing it so often, I want it to be something that you can do quickly and easily without having to put a lot of effort into it. Now, the way these are demonstrated in the textbook, they use the Pythagorean identities, which we have not looked at yet, to help them solve these problems. I'm going to do it based on the function definitions. I'm not going to do it based on identities. So when you do your homework in MyLab and you see instructions that say use the Pythagorean identities to work this problem, you just need to know that that is not the way that we're going to do it here in your notes. So I don't want you to get confused. I just want you to be able to work the problems the easiest way. So what I'm about to show you is reliable and works every time and is less algebra intensive than what you would see in the online help in MyLab. So here's example 5. And it says find the sine of theta and the cosine of theta, given that the tangent of theta is 4 over 3 and theta is in quadrant 3. Now, we always want to start with a sketch because the sketch will really help you get your bearings and understand what you're doing. So let's draw ourselves a quadrant 3 angle. Here's my quadrant 3 angle, and I'll label that theta. And of course, we know that we can close up that right triangle by drawing that little imaginary line back to the horizontal axis. And now let's look right here. They told us that the tangent of theta is 4 over 3. And they actually gave us 2 important pieces of information here by telling us that tangent is 4 over 3. So we know that the definition of tangent is y over x. So that means that 4 over 3 is equal to y over x, and we can use 4 as our y value, or the vertical side of our triangle, and we can use 3 as the x value, or the horizontal side of our triangle. And now in order to find the sine and the cosine, we just need to find an r, because we know sine is y over r and cosine is x over r. So what we'll do now is use the Pythagorean theorem to figure out r. And so we know that r squared is going to be 3 squared plus 4 squared. We know 3 squared is 9, 4 squared is 16. So 9 plus 16 is going to add up to 25. So r squared is 25, and that means r is 5. Now, I wrote it here for you because we're just getting used to this, but I do want you to get accustomed to doing the math for the Pythagorean theorem in your head. So I would actually like it if you could just look at the 3 and the 4 and say, I'm looking for r, so I'm going to need to add the squares. So 9 plus 16 is 25, and then the square root of 25 is 5. And you wouldn't have to write all this down. But look, as long as you need to write it down, keep doing it, but try to get to a place where you don't need to write it down. Okay, so now that we have x, y, and r, we're free to now find the sine and the cosine of theta. So the sine of theta we know is y over r, but we need to keep in mind that in different quadrants, the sine value could be positive or negative. So let's think about ASTC. And we can see that in quadrant 3, only the tangent function and its reciprocal will be positive. So we're looking for a sine value, so we know that's going to be negative. So first put down your negative, and then we can think about y over r. So that would be 4 over 5. So the sine of theta is going to be negative 4 over 5. And then for the cosine, same thing. We know that in quadrant 3, cosine is going to have to be negative, so go ahead and put your negative down first, and then think about your definition, x over r, so that would be 3 over 5. And that was all they asked us to do here, so we found both of the values they asked for, and we're finished. Let's do example 6 together. So example 6 says, find the sine of theta and the tangent of theta, given that the cosine of theta is negative square root of 3 over 4, and the sine of theta is greater than 0. In other words, the sine of theta is positive. So again, we want to start with a sketch, but they didn't tell us outright what quadrant theta belongs in, but they did give us enough information to figure out what quadrant theta belongs in. They told us that the sine of theta is positive, and so from that we know that theta has to either be in quadrant 1 or quadrant 2. And they also gave us a cosine value that's negative. And so if the cosine of theta is negative, it can't be a quadrant 1 angle, it must be a quadrant 2 angle. And so we're going to draw our theta in quadrant 2. And now we'll draw that little imaginary line to the nearest horizontal axis. And of course we want to label our known sides, so let's go to this cosine value that they gave us, Now we pretty much already used the negative sign to determine the quadrant for theta, so we really don't need that anymore, and I'll just use the numbers from this point. So we know that cosine is x over r, and so I'm going to write square root of 3 over 4 is x over r, and so I can use square root of 3 as my x value, which will be the length of this horizontal side here, and I can use 4 as the r value, which will be the length of the hypotenuse. And so what we have to do now in order to know the sine and the tangent of this angle is we need to find the length of the vertical side. And so we're going to use the Pythagorean theorem, and I will write it down for you again, but remember, you're trying to get comfortable doing it mentally, so you're trying to actually get away from having to write it down every time. Okay, so what we're going to do is say we are looking for this leg y, so that means we're going to have to subtract squares. So y squared is going to be 4 squared minus this radical squared. So 4 squared is 16, this radical squared is 3. So 16 minus 3 is going to be 13. And then the square root of 13 is y. So the length of that side is square root of 13. And now we have all the information we need to find the sine of theta and the tangent of theta. So, of course, we want to remember our ASTC, so I'm going to write that over here so we can see it and think about it. We know that we have a quadrant 2 angle, so we know that only the sine function and its reciprocal can be positive. All the other functions will have to be negative. So the sine of theta will be positive, and it's y over r, so it's square root of 13 over 4. And that's all we have to do to that one. It doesn't need to be simplified, rationalized, or anything. That one's final. And now for the tangent of theta, we know that for a quadrant 2 angle, tangent is going to have to be negative. So let's go ahead and put down our negative sign. And then let's think about the definition of tangent, which is y over x. So that's going to be square root of 13 over square root of 3. And of course, for this one, we need to rationalize the denominator. So let's multiply top and bottom by square root of 3 because we want to eliminate that square root of 3 in the denominator. And so to combine these radicals in the top, to multiply radicals together, you just multiply what's under them. So square root of 13 times square root of 3 would be square root of 39. Don't lose your negatives. So we've got negative square root of 39. And then in the denominator, we've got square root of 3 times itself, which is just 3. And so that's the final form for the tangent of theta. And now let's do one more similar one together. This is example 7. It says, suppose that the angle theta is in quadrant 2, and the sine of theta is 2 over 3. Find the values of the other 5 trig functions. So of course, right off the bat, we want to draw ourselves a quadrant 2 angle. And so I've labeled this quadrant 2 angle as theta. And I'm going to go ahead and close up my right triangle with that imaginary vertical line. And of course, we want to label the sides of the triangle. So let's look at the piece of information they gave us here that says sine of theta is 2 over 3. Now we know that the sine of theta is y over r. So 2 over 3 is equal to y over r. So we can use 2 as our y value, and we can use 3 as our r value. Now for this missing leg, let's use the Pythagorean theorem, but let's try to do it mentally and try to not have to write it down. So we're looking for a leg, so we know we have to subtract squares. So the square of 3 is 9, and the square of 2 is 4. 9 minus 4 is 5. That is the square of the missing side. So the square root of 5 is that missing side. And so that's going to be our x value. Now they've asked us to find the other 5 trigonometric functions. I'm going to start with the sine just because I want to have all 6 here when I get finished. So I'm going to put sine of theta equals 2 over 3 right here. And then we're ready for the cosine of theta. And of course, when we do the rest of the functions, we'll need to keep ASTC in mind. So I've drawn it right here. This is a quadrant 2 angle, so only sine and its reciprocal will be positive. That means cosine will be negative, so I'm going to go ahead and put down a negative sign. And then use the definition of cosine, which is x over r. So that's going to be negative square root of 5 over 3. And this is in final form because nothing needs to be simplified, rationalized, or anything like that. And then for the tangent of theta, again, it's a quadrant 2 angle, so we know that the tangent function will be negative. I'm going to go ahead and put down my negative sign. And then tangent is y over x, so that's going to be 2 over square root of 5. Now let's rationalize this denominator because we do need to remove that radical from the denominator. So we'll multiply top and bottom by square root of 5, and that gives us negative 2 square root of 5 over 5. Now for the other three functions, we can just use the reciprocals of the functions we've already found, so we won't need to refer to the diagram anymore. The cosecant of theta will be the reciprocal of the sine, so that's easy, that's just 3 over 2. The secant of theta will be the reciprocal of the cosine. Now remember, when we flip a fraction over, if it's negative, we don't move the negative. You want the negative to stay in the top. So now the secant of theta is going to be negative 3 over the square root of 5, and this does need to be rationalized, so that's going to come out to negative 3 square root of 5 over 5. And then for the cotangent, now look, we have two different versions of this number. We have the rationalized version and we have the unrationalized version. This version in purple that we found just using the definition before we rationalized. Now think about this. If I'm going to flip one of these over, which one do you think is going to be less work to flip over? If I take this final form of my answer and flip it over, the radical will land in the bottom and then I'll have to rationalize again. But if I take this pre-rationalized version and flip it over, I'll have negative square root of 5 over 2, and that answer does not need to be rationalized. You would come out to the same answer if you flipped this over, but you would have a lot of rationalizing and simplifying to do first. So why not go the easy way? Most of the time, it's easier to flip the unrationalized number than it is to flip the rationalized one. And so this is our final form for cotangent, and we have found all 6 functions for theta. And now I'm going to introduce you to some new identities. So these are the quotient identities, and it says for all angles theta, for which the denominators are not 0, the following identities hold. The sine of an angle divided by its cosine is equal to the tangent of that angle. And if you think about reciprocal functions, the cosine of an angle divided by its sine is equal to the cotangent of that angle. This second one should not be a surprise once you know the first one. If sine over cosine is tangent, then of course the reciprocal of the first fraction equals the reciprocal of tangent, which is cotangent. So it all matches up. But I want us to see how this came about. So here we are going to derive or figure out for ourselves the quotient identity. So let's start with sine of theta over cosine of theta. And what we're going to do is switch to the definitions of these functions. So we know that the sine of theta is y over r, and that would go in the top. And then in the bottom of our fraction, we'll have the cosine definition, which is x over r. So this is what you call a complex fraction. And to simplify it, we just need to multiply top and bottom by something that will cancel out these little denominators. So I'm going to multiply the top and the bottom both by r over 1. Remember, we can multiply anything we want into the top of a fraction as long as we also multiply it into the bottom of the fraction, and that way the fraction stays the same value. So I'm multiplying top and bottom by r over 1. So focusing only on the top, we can see that the r's will divide out, and then focusing only on the bottom, we can see that the r's will divide out there as well. And so that leaves in the top y over 1, which is just y, and in the bottom x over 1, which is just x. So this step right here simplified our complex fraction into a regular fraction, and we recognize that y over x is the tangent of theta. And so that is why this identity works. let's do the same thing for the other quotient identity. So if we start with cosine of theta over sine of theta, and we trade cosine of theta for its definition, and then in the bottom we trade sine of theta for its definition, and then multiply top and bottom by r over 1, again the r's divide out, and this time it leaves us with x over y, and we know that x over y is the definition of cotangent. And so again, these are called the quotient identities because they start with a quotient. A quotient is just a fraction. It's just a fancy way to say a division or a fraction. And so these are the quotient identities because they contain a quotient. And now we're going to look at another set of identities called the Pythagorean identities. They're called the Pythagorean identities because they're based on the Pythagorean theorem. And so, of course, there are going to be squares involved. And so I need to show you how to write a squared trig function. Whenever we need to square a trig function, the exponent is going to go after the function, but before the argument, before the angle. So, for example, we know that y over r represents sine. So if we square that, then we could write that as sine of theta in parentheses squared, but mathematicians did not like having to write an extra set of parentheses every time they wanted to square a function, so it was just generally agreed on that instead of the parentheses, we would put that exponent in here. And so we always see it written this way, sine squared theta. But it means this. It means find the function value of the angle and square that function value. But we always write it this way. So I know it looks strange at first, but this is how mathematicians agreed to write it. And again, it just keeps us from having to write the parentheses every time. So here are the Pythagorean identities. You do not need to memorize these right now. We will memorize them later in the course. But for right now, I just want us to get introduced to them. So it says, for all angles theta for which the function values are defined, the following identities hold. Sine squared theta plus cosine squared theta is 1. Tangent squared theta plus 1 is secant squared theta. And 1 plus cotangent squared theta is cosecant squared theta. Okay, now let's look at these a little more closely and see if we can figure out how they came to be. So here's the diagram again, just so we can remember why x squared plus y squared equals r squared. So let's start by writing down just the basic Pythagorean theorem. X squared plus y squared is r squared. Now the first thing I'm going to do, and it won't be obvious why I want to do it, but I'm going to change the order of these two terms on the left. So let's write it as y squared plus x squared equals r squared. I think you'll agree with me that doesn't change the theorem at all. It's still the Pythagorean theorem. I just chose to write the letters in a different order, but that's okay. Okay, now what I want us to do is remember that we can divide the left side of an equation by anything we want as long as we divide the right side of the equation by the same thing. And so let's divide both terms on the left by r squared. And so that means I have to divide the right side by r squared as well. Okay, now we're going to use a little algebra rule which says if you have the same exponent in the top and the bottom, you really don't have to write the exponent twice. What you can do is just put the whole fraction in parentheses and write the exponent once. So instead of writing y squared over r squared, I'm going to write y over r all in parentheses squared. And same thing here, x squared over r squared is going to be x over r in parentheses all squared. Now on the right side, r squared divided by r squared, of course, is 1 because we have exactly the same thing in the top and the bottom. Now that we've written it this way, I'm sure you can see that y over r is just our sine function. And so this is going to be the sine of theta squared, but we're going to write it sine squared theta. And then this fraction, x over r, represents the cosine of theta, but it's squared, so we're going to write plus cosine squared theta, and we know that that sum is equal to 1. And so that's where the first Pythagorean identity comes from. It's just the Pythagorean theorem divided through by r squared. Now let's take our Pythagorean theorem again, and this time instead of dividing through by r squared, let's divide through by x squared and see what happens. And so we'll do the same exponent step again. We'll take our two exponents and just write the fraction in parentheses so that we only need one exponent. And right here on the second term, x squared over x squared this time makes 1. And over here on the right side of the equation, we'll use our exponent rule and write r over x in parentheses and the whole thing squared. Now we recognize y over x as the tangent function. So this is going to be written tangent squared theta. And then we have our plus 1. And then over here on the right side, r over x may not be as familiar at first, but if you think about this as the reciprocal of the cosine function, you'll recognize that this is secant. So this is secant squared theta. And so here is our second Pythagorean identity. Tangent squared theta plus 1 is secant squared theta. And then let's go one more time. We'll start with our basic Pythagorean theorem. And we've already divided through by r squared the first time, and then we did x squared the second time. So this third time, let's divide through by y squared. And so now we see y squared over y squared is 1. Here, x squared over y squared can be written as x over y in parentheses all squared. And on the right side, r squared over y squared can be written as r over y in parentheses all squared. And now we can change from our fractions back to our trig functions. So we have 1 plus, and then x over y is the cotangent function. So x over y all squared is cotangent squared theta, and then equals r over y squared, and we know r over y is the reciprocal of sine, so this is the cosecant function. So that equals cosecant squared theta. And there is our third Pythagorean identity. And that's it for section 1.4. I hope you'll go spend some time on the homework, work back through these derivations a couple of times so that you really understand the identities, and so they'll stick with you better when it comes time to use them later in the course. But that's it for this time, and so I'll see you guys next time for section 2.1. Bye now.